So under drawing process, it is a sheet forming process to make cup shaped, box shaped, or other complex curved or hollow shaped parts. Okay. So under drawing process, what we can make component which are having shape cup shape, box shape, or there may be complex curve and hollow shapes that can be produced using drawing process. Okay. And what we basically do, might be you have studied about drawing process in your manufacturing process also. So you might be remembering that under drawing process, your sheet blank is positioned over a die cavity, and then a punch pushes that metal into the die opening. Okay, so the metal blank takes the shape of your die and punch. Okay, and these the products of this drawing may be beverage cans, uh, automobile body parts, or panels. Okay, and there may be drawing may be to a d to to a very large height. Okay, so there comes into the picture that is the HYD ratio. Okay, so if the HYD ratio is greater than 0.5, then it is called deep drawing, and if the HYD ratio is less than 0.5, then it is called shallow drawing. Okay, so in today's lecture we are basically going to cover deep drawing process. Okay, as mentioned in our syllabus. Okay, so how this deep drawing, first we have to understand how this deep drawing is uh, different from wire drawing. Okay, one may be confused with wire drawing or tube drawing process. So how this deep drawing process is different from your conventional wire drawing or tube drawing process. Okay, so under wire drawing or tube drawing, as we remember, we have initial workpiece which is itself in the form of wire or tube. Okay, but in the case of deep drawing, the initial blank is flat blank. It may be circular or rectangular depending upon our requirement. Okay, so here we are having a circular blank, and it is placed over this die cavity, and a punch pushes this blank into this your die opening. Okay, and after the application of this punch force, it takes some cup shape. This cup shape is visible here. Okay, so the final shape comes something like this in the case of your deep drawing process. Okay, so here I have taken one example of cup drawing. Here you can see a good cup that has been formed using your deep drawing process. Okay, here you can see one fractured cup. So if your blank size of blank is not proper, or the dimensions or the thickness is not proper, then the fracture in the cup takes place, and which may be like this. Okay, you can see in this figure. As well as if the proper blank holding force is not there, then there may be wrinkles on the surface of your final product. Okay, so this is some part which has been shown through some simulation software. Okay, I have taken this diagram from a book. Okay, so now we will try to understand what are the different deformation zone during deep drawing. Okay, so under deep drawing, there are many type of forces and deformation modes that exist in the case of deep drawing. Okay, so under deep drawing, we have tension in walls, and in bottom we have compression as well as friction in the planes, and also bending uh, at the die radius and straightening in the die wall. Okay, So all these complex deformation occurs in the case of your deep drawing process. Okay, so I have taken uh, view of your one component which is under deformation in the deep drawing process. Okay, so here you can see this is your final product cross section. I have taken cut cross section. Okay, so here I have marked 5 zones. These zones are B, B, C, D, then E, F, G. Okay, so up to A to C, I have marked one zone. Then C to D, that is the another zone. Then D to E is third zone. Then E to F is fourth zone, and F to G is your fifth zone. Okay, so what is happening under the zone A and C? There is axial compression because this is your die, and this is a blank holder, and some force is being applied by this blank holder. Okay, so there is some axial compression in this portion A to C, as well as uh, since this is being elongated, this portion is being elongated because of the punch force. There is obviously radial tension, as well as there is circumferential compression in this portion. Okay, between A and C. Okay, so here three kind of deformation or the forces are existing. That is the axial compression, radial tension, and circumferential compression. Okay, so this is about zone A to C. Then we have zone C to D. You can see, I think it must be visible. This is C and this is D. Okay, so this is the die corner radius. Okay, so what is happening here? The bending is taking place. Okay, and as well as there is friction between the surfaces of your die and C. Okay, so there are two things, that there is frictional force as well as there is bending in the zone C and D. Okay, so in bending, as we already studied, there may be compressive stresses as well as tensile stresses. Okay, in the bottom side, that is die side, there will be compressive stresses, and on the upper side, that is the blank holder side, there will be tensile stresses. Okay, then we have this long zone, that is the DE zone. Okay, under this zone is under tension. Okay, so tensile stresses will be there. Okay, and there are potential chances of fracture in this zone, that is the D to E zone. Okay, then we have EF zone. EF zone, that is the contact between the punch and your seat. Okay, so this E to F, sorry, E to F zone, what we are having, there is a punch corner radius, and because of this punch corner, what is happening? Bending is taking place. Okay, so here also there is bending is taking place, as well as there is friction between your punch and seat. Then we have this flat surface, that is which is under the contact of your punch. Here what we are having? We are having friction between your seat seat and punch, and we assume that there is no strain in this portion, but there exists some strain. Practically, there some strain is there, but we assume ideally that there is no strain in the zone G to F. Okay, so these are the different deformation zone that are visible in the case of your deep drawing process. Okay, so now we will try to understand the this mechanism of drawing. Here I have shown 5 diagrams step by step. We will try to understand how this deep drawing or drawing process takes place. Okay, so in the figure 1, this is figure 1, you can see you have a initial blank that is kept over your die. Okay, this is your die. Okay, and this is your die opening. Okay, so what is happening? We have die opening, and we have kept our initial blank over this die opening. Okay, then we have placed blank holding. This is your blank holding, and FH is your blank holding force. So that why this blank holding is provided? Blank holding is provided in order to avoid unnecessary movement of your blank holding, the unnecessary movement of your blank. Okay, this is your initial blank. Then we have punch, which is placed exactly uh, above your blank. Okay, so in the first step, in the first arrangement, we can see the punch is making contact with your workpiece or your blank. Okay, as soon as this punch moves further, it takes what will be initially, if this punch is moving down, these two this portion is free, so the bending will take place at the die corners. Okay, here is this die corner, here is another side. Okay, so bending will take place, and and your workpiece will take shape like this. Okay, so initially what will happen? Bending will take place uh, uh, at the die corner initially. This is your first step in the case of your drawing. Okay, and if we move further, we apply forces. If your punch move further, what will happen? This bend portion will be straightened. Okay, this straightening of this bend portion will take place, straightening along your die wall. Okay, so if in the next step, what we can see there, that is in the figure 3, this bend portion is straightened, and there are tensile stresses generated in this straightened portion. Okay, and if we keep moving further your punch, then in the figure 4 we can see there is thickening of flanges here. Okay, this thickening is taking place because material is not able to flow properly. Okay, or maybe because of frictions between frictional force or blank holding force, or basically it is because of frictional force between your blank holding and your seat surface. Okay, so this thickening is takes place, and this compressive stress is increased in this portion. Okay, and as we continue, the final product that is formed, that you can see in the figure 5, this is your final product, which is showing there may be some thinning effect also. Okay, so in this figure, the thinning effect will be higher at the bottom and lower at your cup surface. Okay, so at this bottom surface, this thinning will be higher, and this may be up to 25%. Okay, so this is how your deep drawing process works. Okay, and obviously uniform thickness is not achieved in the case of deep drawing. Okay. Okay, so now we will come to the next part, that is calculation of the blank diameter. Okay, blank diameter is nothing but your initial diameter of your seat. Okay, so we assume that initial diameter of seat initially it is capital D, and we are forming a cup. Okay, this circular cup we are producing the product which is visible in figure 5. Okay, so we assume that the initial diameter of the blank is D, capital D, and the punch diameter is D. Okay, okay, so what we can see, if we try to you know go mathematically, what we can see that pi d square by 4 is equal to pi capital T square by 4 is equal to pi small t square by 4 into plus pi dh. We this calculation how we are doing, we are assuming that there is no change in thickness. Okay, so we are doing volume consistency. We are assuming volume consistency. For volume consistency, what we will have, suppose T is thickness, then initial volume of your blank will be pi d square by 4 into T. Okay. Similarly, for the portion which is under the contact of your punch, that will be pi small d square by 4 into T and pi dh into T for the for this. Okay. So as we are assuming a uniform thickness, so T will not vary, and we have removed that term. Okay. So which this ultimately result into this is typo mistake. This is not pi. This will result into d square equal to capital D square equal to small d square plus 4 pi dh. Okay. And finally, we can get the diameter of your blank, which is square root of small t square plus 4dh. Okay, this is a type. Yes.
From where that first equation has come? You are saying that we are equating the volume from both the end.
Yes. Okay. Okay. So
But
see here. Yes. Here you can see initial. Okay. Okay. Here you can see this is your initial blank. Okay,
yeah, yes,
here this okay. So if we calculate the volume of this blank, what will be pi d square by 4 into T. This will be volume of this blank na.
yes, sir.
Yeah, right. Okay,
Yes,
and this blank has been converted into this particular shape. Okay, at figure 2 we can see this is your final product. Okay, so for this final product, what will be the volume of this bottom portion as well as volume of this uh, is this portion. Okay, so the volume of this portion will be, since we are assuming that the diameter of lower portion is small t. Okay, so volume of this portion will be pi small t square by 4 into T, right, Sandeep?
yes, sir.
हाँ, ठीक है. So and what about this volume of the remaining portion, this height? Okay, so how we will calculate? This will be pi d h into T, right?
Pi,
Volume
sir, but
of
it's
uh,
area will be pi r square h,
yes, yes, yes.
and for the sake of volume b is to multiply t. Then the area, then
Okay.
the
How we calculate the circumferential area of this circle? This will
pi.
be pi t into h, na?
Yes, sir.
Okay. This, once we have calculated this circumferential area, and we are assuming that this thickness is uniform. So what we have to do? We have to simply multiply it by t. Once we have got the circumferential area, we are assuming that there is no thickness variation. So if we multiply it by thickness, then we can get this volume, na,
Yes,
approximate value. Okay, we are saying approximate value. There may be slight variations. Okay, if we go more accurately, then there may be slight variation. We are continuing with certain assumptions. So we have simply calculated the circumferential area, which will be pi d into h, and it will be once it is multiplied by thickness, it will give volume, right? Okay,
okay, sir.
so this is how your this term has come, pi dh into T, this term, right? So
Okay.
because T is common, so we have removed T, right?
Yes, sir.
T is common in all terms, so I have removed T. Okay, again here this is a typo error. Pi I have wrote while typing. I forgot this from all terms. Okay, so this will be here also. This is a typo error as well as here is also typo error. So if we remove pi, what will happen? As well as we multiplied by 4 also. So what will happen? D square is equal to capital T square equal to small t square plus 4dh, right? This term will come. Okay, forget about this line. This is a there are two typo error, two place pi is placed by mistake. Okay, so if we conclude, what will come? Capital D will be equal to square root of D square plus 4dh, right? So approximate value of blank diameter we can get from your from this formula, right? ठीक है ना संदीप, यहाँ तक क्लियर है?
Yes, sir. Yes, sir.
Okay, so this way we can calculate the initial blank diameter depending upon the requirement of your uh, shape and size of your final product. Okay, and we can calculate the blank diameter similarly for other complex product also using this volume consistency formula. Okay, always we go through the analysis, that is the volume consistency in the case of seed forming processes or any other process. Okay, then we have second term, that is the total punch force. How we can calculate the total punch force? So I am not going with the detailing how this formula has been calculated. We have to simply remember this formula. It is having three terms. This is first term, then second term, then third term. Okay, this first term pi dph under bracket 1.1 sigma 0 natural log of do upon tp. Okay, so this is first term, then second term, then third term. Okay, so I went through a few books and I found what is first term. First term is basically it is punch force due to your ideal deformation, and second term, that is basically appearing because of uh, force due to friction and blank holding pressure. Okay, then there is third term, that is P, that is the force required to bend and straighten your blank. Okay, so you have maybe you may be given these values in during your examination. dph, everything, each term will be given to you, and you have to remember this formula and for calculating your punch force. Okay, so again in the next slide I have mentioned what is do, what is dp, what is, so p is your punch total punch force, sigma 0, this is your average flow stress, then dp is diameter of punch, then do is your meter. Okay, h is your holding blank holding force. Okay, small h is your wall thickness, sometimes you may find it is as t or okay, mu is your coefficient of friction, and b is force required to bend and straighten your plank. Okay, so these all values will be given during your examination. Okay, then we have next topic that in your deep drawing, that is limiting draw ratio. Okay, so this limiting draw ratio is nothing but we can first try to understand what is drawing ratio. Okay, so draw ratio, it may be given as initial blank diameter to the uh, cup diameter. Okay, so suppose D1 is cup diameter of your final product and DO is your initial diameter, then drawing ratio may be given as DO upon D1. Okay, similarly, we can calculate limiting draw ratio. Limiting draw ratio is defined as the maximum DR that can be obtained while drawing a cup without fracture. Okay, so uh, sometimes this limiting draw ratio is a measure of your drawability in case of your drawing process. Okay, so in exam you may find that define drawability, then you have to again define your limiting draw ratio. Okay, so this limiting draw ratio is what is this? This is maximum DR. Okay, so how this can be calculated? That maximum blank diameter which can be converted into cup without any failure. Okay, okay, so DO max is your maximum blank diameter which can be converted into cup without any fracture or defect in your final product. Okay, there are certain factors which affect your drawability or limiting draw ratio. So I have the factors can be which can improve your drawability of your seat or which can increase the limiting draw ratio. Okay, so first is by decreasing blank holder and seat friction. Okay, so if the frictional force between your blank holding and seat surface is less, then your draw ratio will increase or drawability will increase. Similarly, by decreasing the frictional force between your seat and die. Okay, previously it was with blank holding and seat. Now it is between seat and die friction. Okay, then by increasing seat and punch force. Okay, by increasing the friction between seat and punch, then by increasing relative blank thickness to diameter. Fifth one, by increasing the punch corner radius to the punch diameter. Next is your by decreasing the relative punch diameter, that is the ratio of punch diameter to thickness. Then in between different materials, we by using a material with high strain hardening component, that is a material which is having high N value. Okay, so this is how we can increase the your drawability or limiting draw ratio in the case of deep drawing process. Okay, so here I have listed out. I have not went in detailing about that. I will provide some supplementary notes also related to this topic. Okay, so there are what are the parameters which affect the deep drawing process? Okay, these parameters are material properties. Under material properties, we have strength coefficient, strain hardening coefficient. There are geometry parameters like punch corner radius, die radius, punch clearance, then blank diameter, blank thickness. Okay, these are geometry related parameter which affect your drawing process. And then there is interface condition, that the interface is with lubrication, without lubrication, that is the friction conditions during your drawing process. Also there are equipment and tooling, that is speed and blank holder, which affect your drawing process. Okay, so now we will come to the limitations of your deep drawing process. Under deep drawing process, the common problem is that is the wrinkling and tearing, that are the typical limitations of your drawing process. Okay, so wrinkling, it basically takes place on the here also. Let me show you that. Okay, so here you can see this wrinkling is has been generated on the surface of your cup. Okay, so why this wrinkling, this problem of wrinkling comes in the case of your deep drawing? Because there was no proper blank holding force. If proper blank holding force is not provided, then then the this wrinkles are formed on the upper surface of your cup. Okay, similarly there may be tearing also. If your uh, uh, there may be chances of failure that this portion may be teared while drawing, while forming this cup using your drawing process. Okay, so these are two major limitations when we talk about your about deep drawing process. Okay, so there is another one, not a problem, but it is required. Since it is required, trimming may be required to reach final dimensions in the case of deep drawing process. Okay, so this was all about which I wanted to discuss about your deep drawing process. Now we will come to the next topic, that is the stamping or press working. In We have around 15 minutes now, so we will try to complete quickly. Okay, so under stamping or press working, or I think you might have studied these processes, blanking and punching, searing also you might have studied during your manufacturing course. Okay, so I will cover briefly only as a revision. Okay, so under metal pressing or metal stamping, it is a process of forming a shape from a metal sheet, coil, or tube using a press tool and stamping dies. The metal is manipulated to the shape of die to produce precise and accurate component. The press forming process lend itself perfectly to the cost-effective production of large batches. There are three principal operations in the press working that cut sheet metal. Okay, first one is searing, second one is blanking and punching. Okay, so I hope you might have studied all these three processes during your manufacturing course. But as for revision, just to memorize, I will give a small introduction. Okay, searing. It is a sheet metal cutting operation along a straight line between two cutting edges. Okay, here you can see we have die, we have searing punch. Okay, and what is being done, as soon as this punch moves downward, your this component is cut into uh, two pieces. Okay, so this process is typically used to cut large sheet into a smaller section for the subsequent or other operations. Okay, so this is how searing is used to cut large sheets into small sheets. Okay, or smaller section. Similarly, uh, we have other processes, that is the blanking and punching. Okay, so under blanking, you might have studied, and under blanking, the sheet metal cutting, it is a process of sheet metal cutting to separate piece from surrounding stock. Okay, so here the cut piece is the desired part, and it is called as blank. Okay, so here we can see we initially we were having a sheet from which your this portion has been cut out, and it is your desired part. Okay, while in the case of punching, the desired part in the case of punching is reverse of blanking. Okay, so in the case of punching, which is the desired part, this is your desired part, and this is your scrap. Okay, so under punching it is a sheet metal cutting process similar to blanking, except cut piece is scrap and is called a slug. Okay, so this is your cut piece is scrap, while it was desired in the case of your blanking process. Okay. So in the punching, the remaining stock is the desired part. That is, it is the desired part, and it was your scrap. Okay. So under blanking and punching, what is important? We need clearance with certain clearance. Okay. So this clearance is nothing but it is a distance between the punch and die. So here you can see this is your punch and this is your die, and we have clearance C. Okay. So clearance is the distance between your punch and die. And how this clearance is given? The typical values are between 4 to 8% of your seat thickness. Okay. So this clearance is given 4 to 8% to the thickness of your initial seat. Okay. So if this, what will happen if this clearance is not chosen properly? If this clearance is too small, what will happen? Fracture line passes each other, causing double burnishing and larger force requirement. Okay. So if this clearance is very small, then very large force will be required. And if this clearance is very high, what will happen? The metal is pinched between cutting edges, and excessive blur are occurring on the seat. Okay. So here we can see that clearance is required between your punch and die. Okay. Now coming to the blanking and punching process, we can see in the case of blanking, where we will require in the case which has shape and size, your punch need to be of accurate shape. Okay. So in since punch needs to be of accurate shape, accurate size, we will require clearance on your die. Okay. We will increase dimension of your die. But in the case of punching, what is the required part? That is the whole part. That is the this portion is your required piece. So so here the uh, the here in the case of punching, the clearance has to be given on your uh, your die has to be of accurate size, and clearance has to be given on your punch. Okay. So for giving the clearance, we have to reduce the diameter of your punch. Okay. This is how the clearance is given in the case of blanking and punch.